last lesson, I talked about single replacement reactions, in which one element kicks out another element from a compound. Now, in this lesson, we're going to be talking about double replacement reactions. And in a double replacement reaction, what happens is partners completely switch, right? So you've got two elements that are together, another two elements that are together. For example, A is with B, and C is with D. And what happens in a double replacement reaction is they just change partners. So what I call this innies and outies. So the outside elements will join together. Okay, so that is A and D will go together. And the innies will go together. So C and B will go together. Now notice the direction of my arrow. C is going to have to go before B. And the reason why is because C is going to be a metal while B is a non-metal. So remember, your metal always goes before your non-metal. Okay? And that's all there is to double replacement reactions. So let's look at a couple of examples. All right, so I've got copper nitrate reacting with iron 3 chloride. So copper nitrate, I'm going to figure out the formula for copper nitrate up above here. So copper has a 2+ charge. Nitrate is one of my polyatomic ions. It has a 1- charge. And so when I cross the charges, I'm just going to write out the reaction right here. The compound is copper Cu NO3 subscript 2. So that's copper nitrate, and it's going to react with iron 3 chloride. So iron has a 3+ charge. Chlorine is 1-. And so this gives me, when I cross my charges, FeCl3. Okay? So remember, as I'd shown up above, we're going to do innies and outies. So our outside elements are copper and chlorine. They're going to combine together. And then iron and nitrate are going to combine together. Now, something that a lot of students get confused, when I combine these new compounds together, copper and chlorine, iron and nitrate, ignore any subscripts that already exist. So ignore the 3 for chlorine and ignore the 2 for nitrate. I will deal with them later. When I combine new compounds together, what I have to do is I simply have to recross their charges. So copper has a 2+ charge, and it is now going to combine with chlorine, which is 1-. So when I cross their charges, I get CuCl2. Yes, I have different numbers of chlorines. Don't worry about it. We'll take care of it in just a minute. Then iron, which has a 3+ charge, is going to combine with nitrate, which has a 1- charge. So when I cross those charges, what I get is Fe in parentheses, NO3, close my parentheses, 3. Okay? Now, yes, I do need to balance, so let's figure that out. Notice I've got 3 chlorines on my reactant side, 2 on my product side, so I'm going to put a 3 in front of copper chloride and a 2 in front of iron chloride to balance my chlorines. Now I have 2 irons on my reactant side, so I'm going to put a 2 in front of iron nitrate. That now causes me to have 6 nitrates. I have 2 already on my reactant side, so I'm going to put a 3 here. Now I've got 3 coppers, and I am balanced. Okay? So notice in this problem, it asks me to write the complete, the full ionic, and then net ionic reactions. So I've got to do that right now. This right here, what I just wrote, is the complete. That shows the entire reaction. The issue, though, is that some of these substances actually don't do anything in the reaction. They just watch. We call them spectator ions. So in order to know what is spectating and what is actually contributing to this reaction, I need to write out the full ionic and then the net ionic reactions. So if you notice on the right-hand side here, I've got my solubility rules. My solubility rules tell me what substances, what compounds are going to be soluble when they're in solution and which are going to be insoluble. Soluble means that it's going to break up into its ions. It is going to dissociate. They're going to break up and dissolve into ions when they are put into water. Compounds that are insoluble will remain solid. Okay? So the first thing I'm going to do is I'm going to go through this, all 4 of my compounds, and decide which are soluble and which are insoluble. So I'm going to first look at copper nitrate. If I look at my rules, notice it says right here, nitrates, NO3 minus, there are no exceptions, meaning compounds that contain nitrate are always soluble. There are no exceptions. So I'm just going to put an S up above here to stand for soluble. Iron chloride, so I'm going to look and I see that I've got chlorine right here. So chlorides are soluble except when they're with silver, mercury, or lead. Well, iron is not silver, mercury, or lead, so this is going to be soluble. And just as a hint, your reactants are always soluble. Okay, just an easy cheat, but if you want to check yourself, please do. Okay, copper chloride. Again, I look at my chloride rule, and this copper is not silver, mercury, or lead, so I know that this is going to be soluble. So then I look at iron nitrate. I know my rule for nitrates is that they are always soluble, so this is going to be soluble as well. Okay, so I didn't end up with anything that was insoluble. Let's see what this is going to look like. So when I write out my full ionic, okay, to break up my ions, I've got 3 copper ions. So 3 copper ions. Okay. Notice I'm going to get rid of the subscript for nitrate in a second. I have a total of 6 nitrate ions, so I'm going to just put 6 nitrates here. So the 2 goes out front now because I've got 6 nitrate ions. Okay. I've got 2 iron ions, so 2 Fe3 pluses. I've got 6 chloride ions, 6 Cl minuses. Okay. Copper chloride is also going to break up, so I've got 3 copper ions. Okay. I've got 3 times 2, which is 6. 6 chloride ions. Okay, I'm going to run into my table a little bit, but that's okay. I've got 2 iron ions. Okay. And then I've got 2 times 3, 6 nitrate ions. Okay. So that is my full ionic. Now I'm going to write my net ionic. So for my net ionic, anything that stays the same on the reactant and product side is going to be crossed out. So notice, coppers are the same, nitrates are the same, irons are the same, chlorines are the same. So for this reaction, since everything is soluble, there is going to be no net ionic reaction. Because ultimately, if I combine those 2 substances together, copper nitrate and iron chloride, we wouldn't observe anything. Nothing would happen because everything is soluble. Okay, let's look at the next example. All right, for the next question, it tells me barium acetate reacts with ammonium sulfate. Okay, so let's write this out. Barium has a 2+ charge. Acetate is C2H3O2 minus. Okay, so when I cross my charges, what I get is barium C2H3O2 and then a subscript 2 because I crossed my charges. Okay, so that's my first reactant. My second reactant is going to be ammonium sulfate. So NH4 has a +1 charge. Sulfate is 2 minus. Okay, so when I cross my charges here, remember because I'm going to have 2 ammoniums, it's going to be NH4, and I got to put the ammonium in parentheses with the subscript 2, SO4. Okay. Now remember, I need to do innies and outies. So my outies are going to be barium and sulfate. My innies are going to be ammonium and acetate. So let's cross my charges. Barium sulfate. Barium has a 2+ charge. Sulfate has a 2- charge. So when I cross my charges, I get Ba2, SO42, and notice I can actually simplify this. And so what I'll end up getting for my product is just BaSO4. Okay? Plus, I need to do my other product, ammonium and acetate. Ammonium has a +1 charge. Acetate has a 1- charge. Okay? And so when I cross my charges, I just get NH4, and then acetate, C2H3O2, sorry, table. Okay. Now I need to quickly balance. I've got one barium, 2 acetates on my reactant side, so I need to put a 2 in front of ammonium acetate on my product side. I've got 2 ammoniums on my reactant and product side, and 1 sulfate on both sides. So I am now balanced. Okay, so this is my complete reaction, my complete double replacement reaction. Let's now write my full ionic. And to write my full ionic, remember I need to use my solubility rules. So I'm going to look at barium acetate first. Acetates, if you notice right here, acetates are always soluble. There are no exceptions to that rule, so this will be soluble. Ammonium sulfate. So you can either look at your sulfate rule, which is right here, or you can look at the fact that ammonium is always soluble. But sulfates are going to be soluble unless they're paired with strontium, barium, lead, or calcium, which is not the case for ammonium sulfate. So ammonium sulfate is going to be soluble. Okay. Barium sulfate, I now look at my sulfate rule and notice it says it is soluble except when with barium. So this, I finally get an insoluble, yes. Okay. And then for ammonium acetate, both ammonium and acetate are always soluble, so they will break apart. So let's see what this is going to look like. I'm going to break up anything that is soluble into its ions. So I've got barium, I've got 1 barium, and it has a 2+ charge. I've got 2 acetates, and they have a 1- charge, or just minus charge. Okay. Ammonium sulfate is also going to break apart because it is soluble. I've got 2 ammoniums here, 2 NH4+. I've got 1 sulfate, so just an SO form, 2-. Those are my reactants all broken up nicely. Since barium sulfate is insoluble, I'm just going to write it as BaSO4. Okay. My other product is ammonium acetate, which is soluble, so I'm going to break it up into its ions. So I'm going to have ammonium, which is, so I have 2 ammoniums, NH4+, and I have 2 acetates. Okay. So that is my full ionic. To write my net ionic then, I need to cross out anything that stays the exact same on both sides. So notice barium is Ba2+ here, but it's in the ionic compound barium sulfate on the product side. So that does not stay the same. My acetates stay the same, and my ammoniums stay the same. So what I'm left with for my net ionic equation, I finally have a reaction occurring. Barium reacts with sulfate, and it produces barium sulfate. Okay. The important thing, couple of important things to know. The ions that I cancel out, those are called my spectator ions. Okay. And the reason why I need to write a net ionic equation is to show what reaction actually takes place. Because notice up above, since everything was soluble in that reaction, there's actually no reaction occurring. You wouldn't observe anything occurring. But for the second example, you would actually see this solid, barium sulfate, form when you combine barium acetate and ammonium sulfate together. Okay? These types of reactions where you have a solid forming, these are called, this is a type of double replacement reaction, that's the section we're on, but specifically they're called precipitation reactions. And they're called precipitation reactions because a precipitate, a solid, barium sulfate in this case, forms. So for double replacement reactions, we can have precipitation reactions, but we can also have what are called neutralization reactions. And a neutralization reaction is simply a reaction that occurs between an acid and a base. Now you already know how to name bases. Bases are simply compounds that have a metal attached to hydroxide for the purposes of this class. All right, so for example, sodium hydroxide, magnesium hydroxide, aluminum hydroxide, etc. We don't know how to name acids yet. So if you have an acid, and remember acids begin with hydrogen,
for the most part. If you simply have two elements, so for example, if I give you HCl, all right, here's how you're going to name it. You're going to start with hydro, and you're going to add the stem or the main part of that element. So chlor for chlorine, and then you'll end it with ic. So hydrochloric acid would be the name for HCl. If you had, for example, HBr, this would be hydrobromic acid. All right. So if instead of two elements, I have three elements, okay, this is the rule that you follow. Specifically, if you have three elements that include oxygen, then you have a polyatomic ion. So if that polyatomic ion has an ATE ending, all right, what you're going to do is you're going to write the stem of that polyatomic ion and ic. So for example, here, NO3 is nitrate. So the name of it is going to be nitric acid. If instead the ending for that polyatomic ion is ite, like nitrite here, then what you're going to do is you're going to add an OUS ending. So instead of nitric acid, it would become nitrous acid. Right? So this really highlights the importance of knowing your polyatomic ions. Do keep in mind, we only use hydro when we have two elements. If we've got the three elements together because we have a polyatomic ion, then you're going to have just the stem and ic or the stem and s. The way that I remember it, and students came up with this, so please don't blame me for it. If it is just us, it is all right, or it is ite, if it's just us hanging out. But if there are 8 people, then it is ic. That's the way that they remembered it. All right, so if you look here, I want you to write the formula for this acid, so phosphorus acid. So I know since it's an OUS ending, then it's going to be ite for the polyatomic ion. So this is phosphite, so this is PO3, 3 minus. That is the polyatomic ion that I have for my acid. So what I need to do now is I simply need to cross charges. Hydrogen's going to be in front, so it's going to have a +1 charge. Phosphite has a 3 minus charge. So when I cross my charges, the formula for this is going to be H3PO3. All right, let's look at the next one, hydroiodic acid. So I know I just have 2 elements here because I have the hydro in the beginning. So I've got hydrogen here and iodic, iodine. So this is going to be I minus. Okay, so now I need to cross my charges. So this is going to simply be HI. So I knew I'd just have 2 elements because I had the hydro in the beginning. So I knew it was just going to be 2 elements. Here, us, because it was an OUS ending, I knew I had a polyatomic ion and that polyatomic ion had an ITE ending. So let's look at one more example, sulfurous acid. So if I have an OUS ending, I know I have a polyatomic ion and I know that it has an ITE ending. So I'm going to have hydrogen and I'm going to have sulfite. Remember, sulfate is SO4, so sulfite is SO3 because I lose 1 electron. And I'm going to have a 2 minus charge. So when I cross my charges here, this is going to become H2SO3. What if instead of writing the formula, I want you to name it? Let's look at some practice there. For number 4, H2CO3. So CO3 is a polyatomic ion. It is carbonate. It has an ATE ending, which tells me that it is going to have an ic ending. So all I'm going to do is take the stem of that name, which is carbon. So for carbonate, it would be carbon, and I'm going to write it as carbonic acid. HF. I just have 2 elements, so I know I'm going to have this situation here where I have hydro and then my stem with ic ending. So it's going to be hydro, and that's fluorine, so it's going to be fluoric acid, which is not something you want to have on your skin. Finally, HClO. So ClO is hypochlorite. So since I have an ITE ending here, I'm just going to take my stem, so hypochlor, and I'm going to add an us ending. So this is going to be hypochlorous acid. And that's it.
All right, let's look at one other double replacement reaction. It tells me calcium hydroxide reacts with hydrobromic acid. So I need to write the equation or the formula for calcium hydroxide. So calcium hydroxide is 2 plus, hydroxide is 1 minus. Okay, and so what I end up getting for my formula for calcium hydroxide is CaOH2. Okay, and that is going to react with hydrobromic acid, HBr. So notice I've got two different compounds. This is still going to be a double replacement reaction. So I'm going to do innies and outies. My outies are calcium and bromide. My innies are hydrogen and hydroxide. Okay, calcium and bromide, I've got to recombine these. So calcium has a 2 plus charge. Bromide has a 1 minus charge. So this is my product is going to be CaBr2. Okay. And then the other product, I combined hydrogen, which is H plus, with hydroxide, OH minus. A lot of people get confused by the fact that there is a 2 subscript right here. Don't let that confuse you. The main thing you need to know is that you're simply combining hydrogen and hydroxide. So if I were to combine hydrogen and hydroxide, they both have a 1 charge. Hydrogen's plus 1, hydroxide is minus 1. So that would simply become HOH. And another name for HOH is, well, there are 2 hydrogens, so H2O. And notice this problem just asked for the complete double replacement reaction, so I just need to make sure I'm balanced, and then I'm done. So for bromide, I've got 1 bromide on my reactant side, 2 on my product side. So I'm going to need to put a 2 in front of hydrobromic acid. Now I have 2 hydrogens from calcium hydroxide, 2 from the acid, so that's a total of 4. So I'm going to put a 2 in front of water, and I am done. Now, this is a type of double replacement reaction. Okay. Notice calcium hydroxide, any compound that has hydroxide at the end of it, calcium hydroxide, sodium hydroxide, rubidium hydroxide, whatever it might be, that is a base. Okay. And for the most part, not always, but for the most part, when you see a compound that has hydrogen in the beginning, that is an acid. So what I'm doing is I'm combining an acid and a base together, and I'm forming water, and then some sort of ionic compound. Now, another name for an ionic compound is just a salt. So NaCl, which we consider to be salt, that is just one type of salt. We call any type of ionic compound a salt. So when you combine a base and an acid together to get water and a salt, that is called a neutralization reaction because you are neutralizing the acid and the base. Okay, so neutralization reactions and precipitation reactions are both types of double replacement reactions.